All right, so everybody, my name's Chris Johnston. I talked to you a little bit earlier about what I've done. Meteorologist here at the National Weather Service in Reno. I'm going to be talking about an analysis of the Loyalton Wildfire Pyro-genetic tornadoes of August 15, 2020. I'm sure many of you heard about the tornado warning that was issued for this event. We'll delve into that later in the presentation. My email is included below if you have any questions. I would also like to acknowledge the scientists that helped me with the radar analysis and storm survey. Neil LaRue, who works at UNR, he's a professor of atmospheric science. He specializes in this kind of work. He's been doing it for probably I want to say 6 years. Brian Brongs, or Sue here, he helped me with the storm survey. And then Tim Bardsley is our service hydrologist. He also went out with us and sampled some of the soil out there. All right, so let's see if this will work. There we go. So first, I want to talk about wildfire fundamentals. What controls a wildfire? Well, there are three components of wildfire environments. One is weather, which is the biggie. Two are fuels. And the third is topography. In the following slides, we'll delve into the specifics of what's caused the fire, the topography, and the weather that led to the generation of these tornadoes. So how did this wildfire start? Well, let's delve into the weather that occurred on that afternoon. A strong heat wave over the west, associated with a persistent area of high pressure, dried the fuels across the western U.S. This ridge lasted for almost 2-3 weeks, or the beginning parts of August, and actually before that into July. Southerly flow around the western edge of the ridge in combination with the decaying cyclonic circulation from post-tropical storm Fausto caused mid to upper level tropical moisture to be advected northward. So it got advected into California. And you'll see here just little basic drawing put together, but let me put this on. So you can see here we actually had subtropical and tropical moisture actually pulled northward around this old circulation from the tropical storm. And then that high was still centered over pretty much southern Nevada, which allowed that to draw up into the northern Sierra. The moisture that was associated with this actually the next day is what caused the lightning outbreak across central California, northern California, which caused all those wildfires that lasted for weeks to months. So basically, we had lofted moisture, so we had elevated moisture source. Let's get this thing to stop doing this. So we had an elevated moisture source, so the thunderstorms were mainly high-based, with much of the rain evaporating before it hit the surface, since we had a dry subcloud layer. So we could see we had a very dry subcloud layer. We were 92 over 43, and the LFC and this LCL were about at, let's see, like in the mid-levels, up to almost 600 millibars. So it was pretty high up there. So the wildfire was ignited by a lightning strike northeast of Loyalton, near Mount Ina Coolbrith in the Tahoe National Forest that afternoon on August 14th. So just to give you some perspective of where this was, so Reno is right here, Truckee up here, Lake Tahoe's here, this is the I-80 corridor, Sacramento's down here. So this fire occurred about 30 miles north of downtown Reno, northwest of downtown Reno. And you'll see what this convection looked like on radar that day. It was just very, meager cells, nothing to write home about. But up here, just north of Tahoe, that little cell you see there, that's what started the fire. I was working that evening. I want to say I think I put out an SPS on it, but I remember that it might have been 1 or 2 lightning strikes, and it started the fire. It's like, for me as a forecaster, I see a thunderstorm going like that, like a little Peasley cell doing that, and then it starts a massive wildfire. So it was pretty frustrating. So for fuels, there was a mix of timber and sagebrush and grasses. So this is actually the valley where these tornadoes occurred. This was taken, I believe, that evening when that fire came across the ridge. So this was the day before the tornadoes. And there was very low fuel moisture content with the persistent heat and the dry conditions for the weeks before that. The topography was mountainous with several canyons and valleys intermixed. So this is actually Roberts Canyon where these developed. We'll see that topography played a huge role in this, these tornadoes developing from this wildfire. So the wildfire grew overnight to 2,300 acres. So pretty much just expanded to the northeast. And weather conditions became very favorable for thunderstorms again. Very similar setup. Moisture was a little bit pooled more north. But what occurred this day was really remarkable. Atmospheric conditions were nearly ideal for rapid fire growth and the formation of fire-generated thunderstorms, or pyrocumulonimbus, just what Alex was showing with the car fire. The afternoon of August 15th, high moisture content was noted in the mid to upper levels of the troposphere, the boundary layer still being dry. So you can see we're 92 over 40. So very similar to the day before. But if you notice, we have most unstable CAPE of about 560 joules per kilogram. The P-watts are pretty high, very high for this area, 0.81 inches. And then look at that surface RH, 21%. So very similar setup. But now that we have a fire below this elevated moisture source, get all that heat, there's a lot of things that went on this day to actually create these pyrocumulonimbus, and we'll get into that. So the wildfire began to create its own weather. Basically by, I want to say about 11 a.m. to 12, we started seeing extensive pyrocumulonimbus actually building over the mountains. So the wildfire generated a series of pyrocumulonimbus clouds. I'm sure some of you know what that is, and we've talked about it before, but basically a fancy word for a fire-generated thunderstorm. And I want to just show this brief little video from the Bureau of Meteorology from Australia. They do a really good job at showing like how one of these actually forms. Sorry for that ad right there. So it's very similar to, like how a thunderstorm develops. Except in our case, we didn't see very much lightning out of it. It was intra-cloud lightning that really occurred. There was a little bit of rainfall downwind. Actually, we'll see that on one of the cameras when we get into it. But yeah, it's just pretty much terrain funneling and the development of these two bifurcated vortices. And we'll see what happens here in the next video. But I want to show you guys just how extensive this updraft was. So this is from that afternoon. This is from Northwest Reno. So this is about 30 miles southeast of the fire. Let me skip ahead to where it starts getting really interesting. So you can see extensive development. We see a pileus actually developing just like the car fire there, where we're punching through different caps in the atmosphere. So you can see there's a cap probably up about 600 millibars that it's punching through, developing that pileus. But you can just see that extensive plume behavior and tilting of that plume to the east. But you really can see that elevated moisture really easily. And you can see the developing cumulus here, cumulus congestus to the south. So this series of pyrocumulonimbus persisted for about 2.5 hours. We had several updrafts that formed and actually moved downstream. And you'll see that one of the tornadoes actually basically propagated downstream with that one of the pyrocumulonimbus clouds and just continued towards near Honolulu Junction, which is just northeast of where that fire was. But this video goes for another several minutes, so I just wanted to give you guys a quick look at that from that view. The next video is closer to the fire. So this is from Babbitt Peak, which is about 8 miles south of the wildfire. So we're very close to it. And you can actually see just how much smoke there is here. But just extensive development with the fire below. Another Pilius right there. There's a bunch that day. So I was working midnight shifts during this event. So I was asleep when it happened. So I woke up to everybody chatting about it and was just pretty much flabbergasted that it happened. And then here's some photos of the magnitude of the Pyro CB. You can see this was actually taken from an airline. You can kind of get a little glimpse of a Pilius right here. I mean, you can see it's punching through a pretty extensive cap right there. And this was taken, I think, from northwest Reno, looking pretty much straight up at it. And then this was from the Truckee Airport. So, oh, what, about southwest of the fire, like, I want to say about 25 miles. So, see how extensive. You can see the one updraft over here and another. So basically, it's very similar to like a supercell where you get these pulses just continually going up and then they move downstream. So you just keep continuously developing updrafts. So how are these different than other ones that have developed in the past? So this is a lot different than what happened on the car fire. We didn't have a hydraulic jump or anything like that. This just developed because of convective forcing and kinematic environment. So here's a radar animation from our radar, KRGX, which is about 35 miles to the east of the Loyalton Wildfire. And it's atop Virginia Peak at an elevation about 8,394 feet, and that's to the center of the antenna. What we can see here is a period of rapid plume deepening and lofting of pyrometeors. And we can see an arc structure to the plume, which is characteristic of plume in a crosswind. So this is kind of looking toward, if you were like to look at it from a spatial perspective, you're looking to the southeast in this case, where the fire plume is actually moving to the northeast. So that mountain I was talking about earlier is right here. And then that valley, Roberts Canyon, is out here over closer to 395. So if we look at this from below, we can see the arced plume. And here's a video from one of the cameras, the CAL FIRE cameras. So what happened is we had near storm horizontal pressure perturbations, which allowed northeasterly low level inflow to develop. And this low level inflow opposed the mean surface to 6 kilometer winds, which was from the southwest. And the right arrow, which we'll see here, we get these counter rotating vortices that develop. So right arrow is showing an anticyclonic sense of rotation, or a meso-anticyclone associated with the strongest convection and combustion. On the left side, we see cyclonic rotation, or a mesocyclone, that we normally hear about with thunderstorms. As the fire progresses, the anticyclonic portion collapses in scale and increases in intensity, while the cyclonic portion remains there but never gets as strong. The first tornado occurs during this video beneath the meso-anticyclone between 1330 and 1334 in the afternoon. And you can see the clock on the bottom right. The video just started over. What is more remarkable is how the kinematic structure of the lower troposphere allowed for the anticyclonic portion of the storm to become dominant. Typically, you wouldn't think about that. In most environments, it's the right mover with a cyclonically sheared environment, a veering profile with height. So we launched a sounding from our office about 1 to 2 hours after that developed, and it showed a backing vertical wind profile denoted by a counterclockwise curved low-level hodograph. And if you follow supercell dynamic theory by Klemp in 1987, this is back in the day of good old science, this backing vertical wind profile would favor the strengthening of the vertical pressure perturbation gradient, basically on that left-hand side. So this is the vertical pressure perturbation gradient. So this is actually strengthened due to that backing wind profile. And that allowed that part of that plume to dominate. And if you actually go back and look at the surface to 1 kilometer SRH, storm relative helicity, you can see that it's negative. So that's actually indicative of low-level anticyclonic rotation. I mean, these values aren't very, eye-shattering. We don't see a large amount of shear here. We don't see, gigantic numbers. I mean, surface to 3 kilometer SRH is only 138 meters squared per second squared. Something like you would typically see with a tornado out on the plains, especially with a CAPE of 560 joules per kilogram. But a fire is going to add a lot more CAPE to the environment just because it's burning so hot. So this pyrocumulonimbus follows a model from Frick and Roscoe from 1994. Basically, wherein the plume will develop a pair of counter-rotating vortices, one cyclonic and one anticyclonic, like I've said before. So this is similar to a rock in a river, which will create vortices behind it. Those vortices become longitudinal vortices with height. So these guys here, this counter-rotating vortex pair. And then beneath this plume, we can generate wake vortices, or these guys right here. And they're also called shedding vortices that are more rope-like in their characteristic. And that's what probably a lot of you guys saw with the videos and the photo of the tornado that was shown. So this is from Burning Man. You could actually see after they were burning one of the smaller structures down, this exact thing happens where you have shedding vortex columns. And you actually see people down here standing in one of these vortices. So now let's look at a radar analysis of this. The video on the right is a radial velocity plan view from that afternoon during which the 3 tornadoes formed. So this is pretty much from 1 p.m. to about 3:40 in the afternoon. And what we could see here is primary fire, and then we can actually see it bifurcate with time and height, where we get the one anticyclonic side and the cyclonic flank. Along the anticyclonic flank of this fire, we get a sequence of very strong anticyclonic rotations, both embedded in the leading edge of the plume. So we can see here, like right here, this is where the primary mesocyclone or the meso-anticyclone is. And then they lead off and shed out to the northeast. Eventually, that's the tornado, the one that sheds off to the northeast that everybody saw coming out of the fire. So the 2 tornadoes that were generated earlier were actually pretty much just enclosed by the fire. You couldn't even see it because the plume was so dark and deep that the only way you would have saw it is if you were in there, and then that would have been very dangerous. So there were 4 vortices in total, and when I went and surveyed that third vortex that we were looking at, actually I did not see any damage from it. So it's probably more of kind of an elevated vortex. Now this next animation shows the plume structure averaged over the top, which the top part of this is the first 3 vortices. So you can see these vortices extending with height. And the bottom is the 4th vortex, or that stronger shedding vortex that went off to the northeast that everybody saw off of US 395. So the primary anticyclonic vortex had 3 separate vortices with a maximum depth of about 13,000 feet or 3.96 kilometers with a maximum rotational velocity of about 55 miles per hour. So if you think about this in terms of gauge to gauge here, that's 110 miles an hour. So we're talking low end EF2, high end EF1 with a tornado. Just looking at base radar components. Now, the shedding vortex on the bottom was one long-lived vortex with a maximum depth of about 17,000 feet or 5.12 kilometers and had maximum rotational velocity just a little bit stronger of about 56 miles per hour, so about 112 miles per hour. And we'll get into this. So that vortex, that long-lived vortex that occurred for almost an hour, it actually went over relatively wide open fields and it didn't really affect anything. So there was no house damage from the tornadoes. There was no loss of property from that. It was mainly from the fire that burned through there later that evening and into the next couple days. So here are some photos from that fourth vortex that onlookers saw. This is the famous one from basically they're standing on the shoulder of US 395 looking west. And it's just beautiful, just seeing that contrast in colors. And then here's one from US Highway 70, which is just to the north of where that vortex was. And then this one was from the top of, I believe this was from like a hill on US 395 north of Hallelujah Junction. And then this is also from US 395. I think this is looking from the southeast towards the actual tornado. So here's a video kind of summarizing what people were seeing. At the end, there is some strong language, so please excuse that, but I thought this was probably one of the better videos to show what was happening that day. So you can see that extensive rotation anticyclonic there, and there's the deepening plume that's tilted over with height. If you look closely, oh, gotta go back, let's go back real quick. You actually see the tornado right here. And this was at night from Cold Springs looking northwest at the fire. So it had burned pretty extensively that day. It grew, I think it grew about like 15 to 20,000 acres more. And here's some air operations and water dumps on it. And these are actually firefighters that were almost engulfed by the flames. And then you'll see this guy, he actually had a dozer behind, and he just barely made it out of the fire line in time. There's his headlights. Here's the strong language. You'll hear it. So this is right after the tornado dissipated. That's when the fire actually started to move to the northeast. All right, so let's continue with the radar analysis. If we plot this as a time mean perspective, about 1 hour radar data, we can see these features stand out quite clearly. The radar reflectivity is shown on the left and the radial velocity is shown on the right. You can see the anticyclonic and cyclonic flakes, the plume itself, and the ashfall region out to the northeast. So that's what that higher reflectivity, not very high, but 20 to 25 dBz reflectivity. The plume has 35 to about 45 dBz of reflectivity. And on the right, if we look at the radial velocity averaged over time, we could see that there's an enhanced inbound flow towards the northeast along both flanks of the fire, as well as a region of reverse flow that we saw in the first video. If we plot the location of all the vortices, they're right along the anticyclonic shear zone, which you can see here. Some of these vortices are embedded in the leading plume, which is part of right here, and then some of them trail off, which is that tornado that everybody saw in 395. So you got to be thinking to yourself, why did we issue a tornado warning? Well, as a forecaster and warning meteorologist, you have to weigh the pros and cons of issuing a warning versus not. In this case, there were very clear circulation features in the radar velocity field, and even better than some of our best convective days. The warning meteorologist on duty decided 5 things. Said that this was no unusual smoke column. I would agree with that assessment. 2, the shear from its tilted updraft suggested conditions ripe for maintaining strength. He thought about the car fire tornado and the risk it was to both firefighters and the public, as Alex talked about earlier, with several deaths, numerous injuries, and significant loss of property. There was no IMET on the fire yet, since it had just occurred the day before, so no way to communicate to the fire personnel on the fire lines directly. So he needed to heighten the awareness immediately. So he decided to issue the warning. So you could see his words here. At 2:28 Pacific Daylight Time, a pyrocumulonimbus from the Loyalton Wildfire is capable of producing a fire-induced tornado and outflow of winds in excess of 60 miles per hour, was located south of Chillicoot and is nearly stationary. Hazard tornado radar indicated rotation. And the impact, he talked about what was going on. Now that we have precautionary preparedness actions that are just basically they're a template, they just pop up. If we're doing something really quickly, we don't have a lot of time to edit this, but later on we did edit this. So you see there, it says take cover now, move to a basement or an interior room on the lowest floor. Well, obviously in this situation, you would not want to do that. Basically wanted to get this out so that fire personnel got out of the way of this, and then the public would stay out of that area too. And it looked like CHP, California Highway Patrol, and several of the emergency managers out there did a very good job of keeping people away from the fire. So here is a animation of how this developed. In the top left panel, we have reflectivity. The top right panel, we have storm relative velocity. The lower panel, we have correlation coefficient. And then over here, we have ZDR. So you can see the circulations that it start and continue and start to trail off on that anticyclonic flank. So at this point, this is when he decides to issue the warning. So we'd already had several circulations going, but he issued when that stronger vortex started to shed off to the northeast and started moving towards Hallelujah Junction and the highway. So it was basically the reason we issued is just to save lives and property. In a case like the car fire, it might have confused personnel and it probably would have confused the public of what was going on. In this case, there was no way to talk to the people on the ground that were fighting the fire. So we needed to get a warning out over cell phones, over any means of communication. We did get in contact with the chief and the resources on the ground a short time after that, but basically the forecaster was thinking, hey, what do I need to do to get the info out and make sure people are getting out of the way of this thing? So it was the first time in history that a tornado warning was issued for a pyrogenetic tornado. And there were no injuries or fatalities reported. So how was this received by the public and media? Nearly everyone in Reno heard of it that day. I remember my girlfriend coming home going, there was a tornado north of town? Like, I was like, what? I didn't even know because I just woke up from my my nap, getting ready for my midnight shift. But yeah, several media outlets were aware of what occurred. We had nearly 15 calls and interviews that evening into the next day. Sacramento Bee, fire tornado warning. Weather Service issues what could be the first at a California blaze. The LA Times, New York Times, Marshall Shepard with Forbes, Capital Weather Gang, NBC News actually did a video interview with Don Johnson, one of our meteorologists. And several news outlets on TV were talking about it around the region. Freak fire tornado. I wouldn't say it was freak, but it was pretty amazing. So we had to go do a damage survey. Team including myself, our science operations officer, Brian Brong, and our surface hydrologist, Tim Bardsley, were tasked with surveying the potential damage. And since the fire burned extensively through much of that area, we were worried that we might not see a lot of damage. But to our surprise, we did see a ton of damage to trees. And here on the right, you could see massive 100-foot Jeffrey pine tree that got uprooted, and it actually got snapped in half at the top, and then it was uprooted. Several of these tree tops were thrown over 100 feet, in some cases 200 feet downwind and in an anticyclonic pattern. But yeah, we were measuring out the distance that these pieces of tree actually flew from the parent trees. So we observed dozens of trees topped, blown over 2 paths in Roberts Canyon, one in Jeffrey Pines and one in Quaking Aspens up on the hill. And a lot of the trees were actually in excess of 20 inches in diameter. And they were blown in an anticyclonic pattern, so the radar was not lying. And treetops were deposited as far as 120 feet from the remaining trunks. And you can actually get a sense of, when you're looking at all this, like how far the tops of these trees flew. And we didn't see any extensive look of like sandblasting on the ground like Alex noted with the car fire. We didn't see any like sandpaper smoothing of the trees. Really, all in all, when I looked at all this and looked at the damage indicators, it was a high-end EF1 and potentially briefly low-end EF2. So here's just some photos of us doing the survey. You can see a pretty decently snapped tree here. But it's just like it felt like you were on Mars. It was just really eerie. There's actually still some spots burning back there in the forest. But several tops of trees just flown hundreds of feet. There's a really good example of how those trees were snapped. Not as extensive as what happened in the car fire, where they were snapped to like the lowest 3 feet of the tree. That these were actually snapped, like 15, 20 feet up. But you kind of get a sense of the anticyclonic rotation here. So these trees out here are facing this direction, the stuff on the ground, then they start to face more this direction, and then they start to face more this way, and then this way. So you can actually get that anticyclonic sense from where those limbs had fallen. And several uprooted trees. And then these are just kind of like a quick snapshot of what they look like along that path. And these are some of the damaged trees up in the Quaking Aspens. There were several topped trees up there. The path wasn't as wide, but you could definitely tell because that primary anticyclonic vortex just sat there, that at some point there had to have been a shedding vortex that came off of that and caused some damage. And there was definitely a path of damage up there that I noted. And then this is out into the valley where the more photogenetic tornado was captured. And the reason we couldn't actually give it a rating, we gave it an EF unknown, because there was no hints of damage. It was just completely blown over by fire, and it's mostly sagebrush out there, and it didn't damage really anything. So, but like we were looking at the radar velocities, it probably could have gotten up to low end EF2. So here's the damage survey results. We did have 3 tornadoes. So back in Roberts Canyon on the anticyclonic flank, we had 2 tornadoes. So we had first tornado here, second tornado. They're both in that back part of Roberts Canyon. And then that third tornado is just this long tracked guy. There were some hints of, helical scouring on the ground with the tornado, the third one. So it's a little bit easier to kind of like figure out where it went, but mainly using radar indicated rotation is where we plotted this. And then you can actually see the viewing angle of the photographer here and then the videographer up here. But here's the first one. It started at 130 and ended about 134. It was an EF1, 104 miles an hour, about 0.43 miles. Maximum width of 137 yards, so not very, very wide, not like the car fire at all, but pretty extensive to see that damage through those trees there. And then the second, going through the quaking aspens up on the hill, this happened about a half hour later, 204 to 208. It was an EF1, a little bit higher wind speeds, just because to snap those quaking aspen trees, you have to have higher wind speeds since they're actually a hardwood. Path length's very short. It's about 473 feet, and it was only about 20 yards wide. So it was a very small vortex that occurred. And that was what it looked like at the time of the tornado. So you couldn't even see into the plume there. It was actually embedded back way into that plume. And then the third one, this is the photogenic looking tornado from the highway. It was very long track. It occurred from 2:41 p.m. to about 3:10 p.m. And given that we couldn't figure out if there was any damage with it, we had to give it an EF unknown. But the path length was about 4 miles. Max width was 156 yards. And yeah, it went pretty far away. And this is that shedding vortex that just basically comes off of those primary bifurcated vortices and just continues to the northeast. So in summary, the Loyalton wildfire was started by lightning in the afternoon of August 14th. Dry conditions, heat, a backing wind profile, and elevated instability allowed for the perfect conditions to allow for a bifurcated plume dominated pyrocumulonimbus during the afternoon the next day. This is the first ever pyrogenetic tornado warning by any weather service office or anywhere in the world, and there were no deaths or injuries that occurred. Reception was exciting as it made national world news almost immediately. 3 tornadoes formed that historic afternoon with 2 EF1s and an EFU surveyed. The Creek Fire and the Bear Fire, around the same time, they actually produced fire tornadoes also. They were actually higher rated. I think the Creek Fire had an EF2, a couple EF2 tornadoes. The Bear Fire, I don't know what the rating was on that or if it was surveyed yet. But yeah, it was a historic summer for fires out here in the West, and very historic for these pyrogenetic tornadoes. So with that, you got any questions or comments? I'd love to hear them, and thanks for having me.
Anybody have any questions for Chris, or same for Alex too, if anybody thought of something for Alex in the meantime?
So Chris, do you think this is information, what you guys learned, something that would be, I don't know, traced back or sent to Norman for their training, how to deal with these situations? Because obviously wildfires aren't going away, as we all know. So I'd be curious if there might be some additional, more detailed training that could be done to help meteorologists out west.
For sure. I have a lot of friends that actually work at SPC and do work with the warning decision training branch there. I know like one friend, he's actually asking a lot about it. We have Evan Bentley is actually working with, he's a forecaster there at SPC. He's working with me on it. We have talked about it, and it'd be great to develop something to kind of, show, look, you're seeing this, but you have to weigh like I said, the pros and cons, because you don't want to confuse firefighters and public at the same time. And the other issue is a tornado warning doesn't have the verbiage correct in it, in the template. And it would take a lot to get that changed around the entire weather service. There's actually been a lot of backfire from headquarters on it, saying that, well, now not so much. They're more leaning towards, since Neil LaRue is doing a lot of research and showing that this is actually tornadic. This is not just a fire whirl event that's happening, that we should start developing a way to warn these guys if we can. So yeah, I think in the coming, it'll take a while, because it's the government and the weather service. The next, like 5-10 years, I could see something like that happening.
Yeah, these fire tornadoes are kind of like the similar scenario to what sprites were for pilots for years. Nobody wants to talk about it because that's a crazy idea.
Yep.
So.
A question, maybe you mentioned this, and if you can summarize it in a short answer, maybe you can't. What is the reason for those shedding vortices?
So it's just like obstacle flow in a river. And let me go back to that slide so you can see. Let me share my screen again real quick.
They're kind of like wake vortices, right?
Yeah,
like
exactly.
wake vortices coming off the wings of a plane or something.
Yep.
Okay.
That's exactly what they're like.
Okay.
But yeah, so in this plot right here, that inbound flow, so basically you got that southwesterly flow on the outside flanks, but you got that reverse flow here. So that's actually what generates those shedding vortices, is you basically get that reverse flow, and that's how they start to just come off. But the way that they come off is because the pyrocumulonimbus actually starts to move downstream. So if there's something that's already pendant with it, like a regular tornado, it's going to start moving with that pyroq.
Okay. Thanks.
If that makes sense.
Yeah, it does. Thank you.
Yep.
Anybody else has any other discussion?
One question I had was,
there we go, Brad.
So it sounds like sounds like the wake vortices in a fire situation don't necessarily occlude like a supercell tornado would. They actually follow the downstream flow of the kind of the pyrocumulus forward flank or whatever. So that seems like that's totally different behavior than a regular supercell.
Yeah, exactly. Yeah, it almost reminds me of kind of like a like a land spout almost, where you can see it just moving with an updraft basically, and that's what's happening, is it's moving with that updraft. It's dependent to that updraft that's tens of thousands of feet in the air, and moving downstream with it. I mean, this is really new research. I think maybe in the last 3-4 years at most that people have been starting to look at this.
I think Brad's gonna go chase it next time. Right?
I was so mad, like, being asleep, I'm like, that just happened, like 10 miles away from me. I'm like, come on, give me a break. So kind of miss chasing, as I haven't been able to get out because I've been out here out west.
That's a cool bucket list item there.
For sure.
Yeah, I think if you can get the perfect stationary supercell, you could probably somewhat mimic, you know, what's going on at the fires, but the environment's just different. You know, you're talking much drier air usually,
Hmm.
and such a heat source. I mean, it's just, it's not like you have a bed of clouds and a little hole that's just going to create a heat, you know, spot on the earth in an area that it's got a lot of moisture. So it's just a whole different ball of wax, I guess.
Yeah, out here in the Midwest, it's moisture, instability, and lift. You don't have much moisture in the interior West.
Nope.
Yeah.
I think we've had maybe, I don't know, Alex, how many tornadoes have we had since you've worked here? Maybe like 2 or 3. Like
Yeah, maybe
Hawthorne and
3.
yeah,
Tahoe,
Tahoe, yeah,
Hawthorne.
water spouts. So
Yeah,
nothing
and then,
supercellular besides Hawthorne, really.
yeah, and there was one out east of Sparks, but unconfirmed. But yeah.
Yeah.
Not very many.
Well, I really appreciate your guys' time tonight. You really outdid yourselves. I think we clocked you in at what time we got here. That was an hour and 35 minutes between the two of you. So, but not a dull moment. It's a lot of good info, and I don't know, Chris. Following Alex is pretty tough. I think he probably should have went after you, but you had more guts and info on it. So
Yeah, I was getting more into the nitty gritty of the science.
yeah, both had their good parts too. So your
But
gifts
I
are in
like
the mail, and hopefully you'll share a screenshot of you two flashing mugs together and sometime next week or so.
Social distancing clashing.
Sure. Likewise.
Well, great to see you, Jared. Thanks for having us.
Yeah,
Yeah,
always a
everybody.
pleasure. So I hope to see you at a few of these future meetings we got in the pipe works here. For anybody else hanging around, yeah, we got the Twister Sisters next month. They're doing kind of a mini case study on that particular tornado by Ashby on July 8th from this year. And then following the tornado trend here for our season, we got Victor Gensini from Northern Illinois University, and he's going to be doing kind of an interesting piece on, from what I understand, from what he told me, is going to be somewhat like tornado climatology, tornadoes past, present, and future. So
Yeah, I know he does a lot of research with climatology, kind of like Jeff Trapp does at Illinois.
yeah, so it'll be a little bit of a different take, and he's chock full of information. So I encourage y'all to make it to those next few ones, and following ones after that. So, all right, well, everybody have a great evening. Thanks for showing up tonight.